So now, to give supplementary explanation about the table of contents. On the first book cover, I said that spacetime is curved. And that things like the waters of the West Sea stick to the surface. Then, how can we know that the spacetime in which we live is curved? How can we find that out? That is something we can indeed know. How? That is exactly what the Riemann curvature tensor explains. We are living in a world where the time and space we inhabit are curved. How do we know that? We know it like this. Here, there are two pens. The pens are identical pens. The way we know that time and space are curved is through this. Here I am, with two identical pens. One goes this way. Then it turns at a right angle and goes this way, and then it turns at a right angle again and comes here, and a slight difference appears. If time and space were not curved, then going this way, then that way, then coming back here should be identical, there should be no difference. But in a world where time and space are curved, if you go like this and then like this and then like this and come back, a difference arises. Therefore, the time and space on the Earth's surface where we live are curved. They are curved by the mass of the Earth, that massive lump of mass. This is a fact. This is explained that way by the Riemann curvature tensor. And another piece of evidence that the spacetime we live in are curved is this. The reason we feel it directly on our skin is the time difference of GPS satellites. So when we drive cars, we all use GPS, don't we? Therefore, if we do not correct for the time difference caused by curved spacetime, in the case of Earth, if GPS corrections are not applied while driving a car, there will be an error of kilometers in the destination in a single day. These are the kinds of evidence that show our world's spacetime are indeed curved. There is a common misconception involving Newton's law of gravitation. When we talk about GPS satellites' motion, we confuse the motion of ball tied to a string. But the motion of the swinging ball and the motion of a satellite are different. Most people misunderstand this point and get it wrong. The rotation of a ball tied to a string and the uniform circular motion of an artificial satellite around Earth's center, those are completely different. Yet ordinary people usually think otherwise. The ball rotating on a string traces its path due to the string's tension. That is, centripetal force. The ball but a satellite is not like that. A satellite has neither centrifugal force nor centripetal force. As I will explain later, from the satellite's own perspective, it is moving in uniform straight-line motion. This is where people are often mistaken. Nearly % of people misunderstand this. You will realize that the motions of satellites and of swinging balls are completely different. I will explain that later. Now then, I have prepared a PPT for today. And the PPT is the same as the one I used last year and earlier this year. This time, I will make the PPT clearer and reinforce the audio to record it again. If I briefly show you the PPT, on the next page. This shows the rectangular coordinate system that represents absolute spacetime. The matrix expressed here is simply another way of representing the rectangular coordinate system. This matrix represents absolute spacetime. It is called the metric tensor, and it represents absolute time and absolute space. This tensor forms when there is no matter or energy in the universe. Such a coordinate system does not actually exist, but we show it because later, when deriving the gravitational field equations, this will be used. In mathematics, it is called a boundary condition. When you go far away from any matter so that its influence is negligible. The system approximates this kind of matrix. Therefore, we use it for that purpose. And in the first PPT I explain the coordinate system of absolute spacetime. Next, in the second PPT, I explain the Michelson-Morley apparatus. General relativity originates from this very experiment. That is why this experiment is extremely important. This experiment is the one that led to both general relativity and special relativity. Therefore, I explain it in the second PPT. In the third PPT, based on the Michelson-Morley experiment, we explain how time and space change in a uniformly moving frame. As seen from the perspective of a stationary observer. That is exactly what special relativity is about. It shows that time and space can indeed change. But they are not the same everywhere, and this is the first entry point. That is what the third PPT covers. Then it goes on to discuss gravity. This is how it works. Time and space are all different, varying from point to point. And in such a world, velocity must be defined differently. This is exactly how it should be defined. It is called 4 velocity, and I will explain it later. Then, in the next PPT, we return to the coordinate system representing absolute spacetime. The rectangular coordinates mentioned earlier. When matter and energy exist, spacetime becomes curved. And this curved coordinate system is what is shown here. So, does the coordinate system really curve like this? Yes, it does. Near the solar system or Earth, we cannot observe such pronounced curvature. It appears almost flat there. But near a black hole, the coordinate system actually curves in this way. Therefore, in a curved coordinate system, the way we approach one coordinate system versus another becomes different. And here is where covariant and contravariant. Covariant vectors and contravariant vectors come from. That is what this PPT explains. So then, since time and space are curved, how can we mathematically represent that curvature? That is what we are explaining here. And that is exactly what the metric tensor is. As I explained earlier, this represents the world of absolute time and absolute space. But the metric tensor of curved spacetime is expressed in this way. So the metric tensor is nothing other than a way to describe curved spacetime. Here it is curved, there it is curved, everywhere curved differently. So how do we represent that mathematically? This is how it works. Between one point and a neighboring point, the relationship of their basis vectors, the relationship of changes in basis vectors between adjacent points. That is exactly what the metric tensor describes. Using such a metric tensor, we represent the coordinates of time and space. That is what this PPT explains. Then in the next PPT, it explains how, in curved spacetime, in curved spacetime, in curved spacetime, in such curved spacetime, how we can bring that world into mathematics. To represent that, tensors are necessary. So on this page, I explain what tensors are. And then Christoffel appears here as well. Christoffel symbols. Then, on the next page, in such a curved coordinate system of spacetime, how will all objects in the world move? This is explained in this PPT. This is the famous geodesic equation. In a world of curved spacetime, how will an object with no external force move, along what path? That is what this explains. In this PPT, then in the next PPT, in such curved spacetime, I explained earlier this concept, called the Riemann curvature tensor, and now I go into detail about it. While explaining it, the Bianchi identity comes out, and from the Bianchi identity the gravitational field equations are derived. Then, in the next PPT, earlier I said, matter and energy curve the surrounding time and space. Then, the matter and energy that curve spacetime. How can we describe that? That is explained in this PPT. And to represent it, we use what is called the energy momentum tensor. That is explained here. So if you look at the gravitational field equations, this is the energy momentum tensor. And this describes how spacetime, depending on the distribution of matter and energy, is curved in its surroundings. That is what the gravitational field equation expresses. That is what this PPT explains. Then in the next PPT, then from here, part begins. Part is about applications. there, as a representative case? If there is a spherical body, like Earth, how will the surrounding spacetime be formed? That is what is covered in part of this book. Specifically in Chapter. In Chapter, the spacetime surrounding such a sphere is calculated. What we calculate is the metric tensor. The metric tensor tells us, when there is a spherical body like Earth, how spacetime is distributed around it. To calculate it is to determine, at a point in that spacetime and its neighboring point, the relationships of the basis vectors. And the result we obtain is this. The metric tensor is expressed like this. When there is mass in a spherical body, this is how spacetime is distributed around it. This is what we calculate here. And because it was solved by Schwarzschild, it is called the Schwarzschild metric. In Chapter, we will solve this directly. Then, on the next page, another application is given, which is the perihelion shift of Mercury. This is explained there. First, Newton explained it as the orbit of Mercury under only the Sun's gravity. That is how he derived it. And then, Einstein explained that, because spacetime is curved by the Sun, how then does Mercury move within that curvature? What kind of orbit does it trace? That is what is solved here. As I said earlier, in a curved coordinate system of spacetime, the motion of objects without external force is determined by the geodesic equation, or the geodesic line equation. Using that, the orbit of Mercury is derived. That is what this PPT explains. Then, on the last page, the deflection angle of light is shown. This is also detailed in Chapter. There, it is fully solved and explained. So I will explain that as well. And the time difference of GPS satellites is also explained in Chapter. So, in Chapter, the full chapter is available on Amazon Books. Please read it when you have time. At first, you may not understand it very well. But since the occurrence of GPS satellite time differences is widely known, reading it will still be helpful. So later this afternoon, I will explain all these things step by step, one by one, in order.